And lesson 21 involves prime and composite numbers and prime factorization. First vocabulary is counting numbers. Counting numbers are the numbers that we use to count. We don't use 0 to count. I wouldn't count the desks in my room 0, 1, 2, 3, 4, 5, because that means that one desk would be a 0, and that doesn't make sense. And it doesn't make sense when you're counting people either. The second vocabulary that you need to write down is prime numbers. And prime numbers belong to the counting number family. They are counting numbers greater than 1, though, because 1 is not included as a prime number. A counting number greater than 1 with exactly 2 factors, 1 and itself. Note, put this in your notes, underline it, circle, whatever you need to do so that you remember. 1 is not a prime, nor is it a composite. And I'll talk a little bit more about that later. Another vocabulary word that's important to know is composite numbers. A composite number is a number with 3 or more factors. For instance, the number 4 has the factors 1 and 4, but it also has a factor of 2. So that's 3 or more factors. Now this little chart is kind of nice because it kind of helps you to figure out numbers between 1 and 10, and then you can always go on further than that. But these are the numbers that I thought I would cover today, and you can kind of take a look at them. We're going to identify counting numbers, prime numbers, and composite numbers. Okay, 1 through 10, those are all counting numbers, every single one of them, because you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if you notice, 1 only has one factor, itself, period. So it doesn't qualify as a prime number, it doesn't qualify as a composite number, and so we're going to just say it is neither. So we really can't count it. It is either one of those. Okay? 2. Now, the only way we can get 2 is to take 1 times 2. Now, if you remember your definition of a prime number, it has only 2 factors, 1 and itself. So 2 is prime. 3, 1 and 3. No other way to get 3, so it is prime. 4 I talked about earlier. You can get 4 by multiplying 1 times 4, but you also have to remember that 2 times 2 is 4, so it is a composite. 5, 1 times 5 is 5. Those are the only 2 factors, so it is prime. 6, 1 and 6, but also 2 times 3, so it is composite. 7, 1 times 7, that's the only way you can get 7, so it is prime. 8, 1 times 8 is 8, but 2 times 4 is also 8, so it's definitely in the 3 or more category, so it is a composite. 9, 1 times 9 is 9, 3 times 3 is 9, and therefore it is a composite. And of course 10, 10's got 4 factors, 1 times 10 and 2 times 5, so it is definitely a composite. Now we're going to make a list. The primes fall into the category of, there we got 2, 3, 5, and 7, right? Those are the only primes. So we have 2, 3, 5, and 7, and that's between 1 and 10. Now you get past 10, there's more primes, of course. In the composite list, okay, the composite list, we have 4, 6, 8, 9, and 10. Those are all composites between 1 and 10. Now, there's only one on this list that counts for neither, and of course it is the number 1. So I'll let you take a minute and write those down. Here are the primes. Here are the composites. and 1 is the one that will not fit into either category. Now, we're just going to talk just a little bit about factor pairs because they just fit right in with what we were just talking about. A factor pair is a listing of two numbers, or a listing of a pair, which is a factor pair, two numbers that multiplied together make another number. For instance, 1 times 2 is 2. So that's a factor pair. Example, when we get into some larger numbers, if we take 14, for instance, it is a composite number because there's more than 2 factors. You can get 14 by taking 1 times 14 or 2 times 7, which I've been saying that way on purpose. So the pairs are 1 times 14 and 2 times 7. 17, remember, it is a prime because it can only be gotten by multiplying 1 times 17. So the only factor pair for 17 is 1 times 17. 21, however, has more. 21 has 1 times 21, which is the one you would expect, and then it also has 3 times 7. So if you look over here, you have 1 times 21 and 3 times 7 as your two factor pairs for 21. Factor pairs aren't that difficult to deal with. They're not that hard. We've kind of been doing them a little bit when we've been working on factoring, so it shouldn't be all that hard for us to do. Now the next thing I kind of want to talk about is perfect squares. And perfect squares, they have one set of identical factors. And we already have run across that a little bit when we were talking about 4. 2 times 2 was 4. 3 times 3 was 9. And when I listed those, you'll notice that I did not list them twice. I only listed them once because I knew we were coming to this part of the discussion. So perfect squares have one pair of identical factors, therefore they will have an odd number of different factors, like 1, 3, and 9, okay, and 1, 2, and 4. Technically, it's 1, 2 times 2 and 4, but we just list the factor that's squared once. Examples, 25 is 1, 5, and 25. We list the factor pairs as 1 times 25 and 5 times 5. Okay, now prime numbers, as we've already discussed, have just one pair of factors. An even number of factors is a pair, and that would be, for instance, 1 times 7 is 7, 1 times 11 is 11, 1 times 17 is 17, 1 times 23 is 23. Those are all factors, and they're in the even pair. Okay. Now we're going to talk a little bit about composite numbers. We've already been working with composite numbers. We just haven't really discussed them very much. This says that every composite number can be written as a product of primes. How do we find the prime factorization of a number? Well, there's two ways. You can use factor trees, or you can use downward division. Factor trees are very efficient, and so is downward division. I'm not trying to sell you on downward division, but I'm hoping that maybe you will see that it is very useful for more than just factoring. Alright, factor tree looks like this. Start with the same number, 42. Take 2 into 42 because you know it's divisible by 2 because it's even. 2 times 21, and then you have to look at 21. 2 plus 1 is 3, and 3 is divisible by 3, so it has to be divisible by 3. 3 times 7. Or you can go over here and use the downward division and go 42, 2 into 42 is 21, 3 into 21 is 7, 7 into 7 is 1, and of course we don't use 1 as a factor when we're writing the prime factorization because 1 is not prime. So when you write your prime factorization, you should never include 1 because it is not a prime. Okay? Okay, so when you are doing factor trees or downward division, you should always use the smallest prime number first to factor it. Both factor trees and downward division are efficient, and both will find the prime factors of a number. It works. They both work very well. All right. I'm just going to show you quickly another set of factorization so you can see it. Proof that they both do the same job. 36, back to tree, 2 times 18, 2 times 9, 3 times 3. Circle the numbers that you end up with on your tree. It will give you the prime factorization. Same way here, only I think downward division is sort of nice because you take 2 into 36, 18, 2 into 18, 9, 3 into 9, 3, 3. Right here in a list from smallest prime to largest prime is your factorization. But hey, you've got it over here too. Both ways work. Which one do you like? Try doing 2 at one time with the purpose of finding the prime factorization of two numbers and then finding the greatest common factor of the same two numbers. So here we go. I'm going to do 70 and I'm going to use downward division because that's the one that I enjoy the most. That's the one I like. But you choose what you'd like to do. So 2 goes into 70. I know that's 35 because 35 and 35 makes 70. 5, 6, 7, 8. This is not divisible by 2 or 3. It is by 5 though, and 5 times what is 35? I think it's 7. And 7 goes into 7 once, and there you go, and you're done. 360, wow, that's a big number. 2 goes into 360. How many times? Let me think. Well, I don't know off the top of my head, but I could find out because 2 goes into 3 one time with a remainder of 1. 2 goes into 16 8 times, and that's with no remainder, so 180. It's even, so I'm going to do it again. 2 goes into 18 9 times, and you have a 0 there. 2 goes into 90 45 times, and then I can't divide it by 2 anymore. 5 and 4 do add together to 9, so I can try 3. 3 goes into 4 one time with a remainder of 1. 3 goes into 15 5 times. 3 goes into 15 5. 5 goes into 5 once, and I'm done. Okay, so I've done the prime factorization of both of these numbers now, 70 and 360. Okay, let's go ahead and write out the prime factorization real quickly. We have for 70, we have 2 times 5 times 7. Okay, 2 times 5 times 7. For 360, we have 2 times 2 times 2 times 3 times 3 times 5. Wow, that's a long one. However, we can now look and see, are there common factors between the two of them? Yes, there's a 2 here and a 2 there. Any more 2's on the top? Nope, nope, nope. Any 3's on the top? Nope, 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 nope. Any 5's on the top? Yep, there's 1 5 here and 1 5 there. Any 7's on the bottom? Nope, there's no 7's on the bottom. So we are done. Now, we just have to look. Okay, greatest common factor. We would take the 2 and the 5, and we're going to multiply them, and we're going to find the GCF is 10. And that's just a really slick way of finding the GCF without having to do a whole bunch of multiplication up here on the top. Multiply 7, try to figure out what the factors are. This is a really slick way of doing it. It works just about every time. Now, here's some nice down and dirty rules that you can write down in your notes. How do we find them? How can we use the prime factorization to find the GCF? First, find the factorization of both numbers. List them out, just like I did up here, right here, okay? List them out, okay? Identify the shared factors. If you look down here, I have the same thing written down. 2 and 5, 2 and 5, identified those, right? So then I wrote them right here, 2 times 5. Multiply the shared factors to find the greatest common factor, or GCF. Step 3, multiply them. 2 times 5 gives you 10. Really is a quick way to find GCF, especially if you have two numbers that you have absolutely no idea what their GCF would be. Okay, now you can try this one out on your own. I don't think I'll take the time to do it because I don't want to extend our video anymore. But if you want to try this one out, it is really pretty quick and easy. So try it on your own. If you have questions and you can't get it, I will tell you that the GCF of these two numbers is really not too big of a number. It's kind of an interesting thing. You would think that it would be really big, but the GCF is only 5. Okay, one last question. If a whole number greater than 1 is not a prime, then what is it? Do. Oh, yes, of course. It's a composite. Well, thank you all for listening. You guys have a great day, and I will talk to you soon. Goodbye.